on contamination. My name is Professor Naho Mirumachi, and I work at the Department of Geography at King's College London, as well as the co-director of the King's Water Centre. And I'm very delighted that I'm joined with my co-director, Katie Meehan. She's on the screen, yes. And she'll say a few words at the end to let you know what kind of activities we're doing, and very much welcome you into our community. We are an interdisciplinary research center, and we're very much interested in looking at water sustainability issues, really trying to take on a fresh, curiosity-driven approach, and also linking science into policy to community action, so that we can implement some sort of change and solution, be part of the solution. We have a policy brief series, which you can access through our website, but alongside that, this webinar event is to add to this depth and breadth of the conversations that I think are pertinent to some of the contemporary challenges that we have today. So in the 1 hour, we'll be covering a range of topics, a range of perspectives on water contamination. And I think I'm particularly curious and keen to learn more about this because here in the UK, where I'm based, there's been a lot of news coverage about raw sewage being dumped in our rivers. And there's been a lot of concern about water quality and the impacts to our rivers, to our ecosystems, and also more generally, I think there's been increasing discussion about what kind of climate change impacts there could be to our water, not just in terms of quantity, but also quality. So I thought it would be a good moment to learn from different experts in the field. And I'm very delighted to be joined by Dr. Luigi Margiotta Castellucci, who is a senior lecturer in toxicology at King's College London. He's also part of our King's Water Centre. And his research is aimed at understanding the mechanisms by which chemicals in the environment can cause adverse health effects, and at developing innovative predictive approaches to support chemical safety assessment. He works regularly in collaboration with industry partners and advises scientific and governmental agencies on the application of integrative toxicology concepts for the protection of environmental and human health. So I'm really looking forward to hearing about what's the latest in his field, and maybe throughout the conversation that we have after his presentation to hear more about experiences working with societal partners as well. Our second speaker is Dr. Carrie-Jean Ormerod, who is an associate professor in the Department of Geography at University of Nevada, Reno. So thank you so much for joining us across multiple time zones. She works broadly in areas of cultural geography, political ecology, and water governance. She has specific expertise in water law in the US West, reclaimed water, and public perceptions of risk. She draws on a range of data and methods in her work, including archives, interviews, surveys, and Q methodology. So we'll have, I think, a very interesting insight into what's happening in the US, some debates around public trust and water recycling. So without further ado, I'm going to give the floor to Luigi. I'm just going to let everybody know that we're recording this, so if people couldn't make it, they can catch up on our website. But without further ado, Luigi, the floor is yours. I will stop sharing my screen and you can share yours.
Thank you.
Yep, we can see your screen.
Perfect. Okay, good afternoon, everyone. To close this, and it is a great pleasure to be here today to share with you my perspective on an issue that affects environmental and human health at global level, and that is the unintentional release of human pharmaceuticals in the environment, and in particular in the aquatic environment. Many scientific papers and reports often refers to these compounds as emerging contaminants. And this was true when I started my PhD 16 years ago, and it still happens today, in the sense that the importance of these compounds has been emerging only recently. However,
We will shortly be arriving at Stevenage.
I've only been a little puzzled by this definition, so I decided to start this short presentation with a little story. So I invite you to travel back in time with me. We are in 1978, and the biologists working at the water company Thames Water noticed a strange phenomenon in fish caught in the River Lee, which is a tributary of the River Thames, so not far from London. In the fish caught in this river, the male fish appeared to be feminized, and the testes were smaller than usual and contained both sperm and eggs. And that at the same time, the ovary of females were also larger than expected. At the time, Thames Water was a public authority owned by the British government, and it reported directly to the Ministry of Agriculture, Fisheries and Food. So research on this matter continued internally and probably confidentially for the following 15 years. At that point, a senior fishery scientist working at the ministry, Dr. Colin Purdom, got in touch casually with an academic colleague that was working on the hormonal control of reproduction in fish. And that colleague was Professor John Sumter at Brunel University, London. And this casual encounter kick-started a collaboration that led to the first scientific paper on this matter in 1994, 16 years after the first observation. And that scientific paper demonstrated that the contraceptive pill, the component of the contraceptive pill, ethinyl estradiol, is a very potent feminizing chemical in fish species. After the publication, the group of Professor Sumter, including Professor Charles Tyler and Professor Susan Jobling, led some pioneering research in the field of estrogens in the environment. Now, I invite you to fast forward in time to 40 years later. And what do we know today is that world's rivers are contaminated with pharmaceuticals, and about 1,000 different pharmaceuticals have been detected in the aquatic environment and in rivers worldwide. Our analytical capabilities are such that we can measure these pharmaceuticals both in the water and inside the organisms of wild species. And we can measure tens of them with one single analysis. At the same time, we can sit at our computer and predict with high accuracy the concentration of all these pharmaceuticals in many rivers, in particular in Western world. And that's because the emission of pharmaceuticals is very predictable, because the main emission source is us, people, patients. After consumption, we excrete these pharmaceuticals and they're metabolized via urine and fishes, and they reach the wastewaters and then the aquatic environments. But how do we establish whether this concentration that we see in the environment are safe? So when we talk about wildlife, we do the environmental risk assessment of pharmaceuticals is based on two simple concepts. From the one side, we predict what's the environmental level of these contaminants are in the water. At the same time, we run a series of laboratory tests on a selected set of species, including crustaceans, fish, and algae, to determine what concentration of these pharmaceuticals do not harm fish. And once we have these two information, we compare them, and in order to be defined as a low risk, a pharmaceutical concentration in the river needs to be lower than that predicted to not cause any effect in wildlife. That's because in this way we are certain that we have a high probability that the environmental levels are unlikely to cause any biological effects. In a similar way, we can also predict the safety for humans and for traces of pharmaceuticals detected in drinking waters. In this case, the comparison is much simpler because we use the concentration that we have in drinking water, and we interpret this concentration in the context of the human drug safety data that we developed during the drug development and discovery phases that are largely based on human directly. So it's an easy comparison, okay? However, it seems that we have everything in place, but we still know very little. So we colleagues at the University of Exeter and the pharmaceutical company AstraZeneca, we extracted and looked at all existing data for all pharmaceuticals on the market. So we considered 975 pharmaceuticals prescribed in the UK. And what we found is that a full ecotoxicity data set is lacking for 88% of these compounds. So we know very little about many compounds, in particular those that have been put to market before 2006. And the message of this paper was that we need a scientifically sound prioritization approach in order to identify those compounds that we should advance forward for priority testing. Then using the data that we had, the information available, we ranked the risk of all these pharmaceuticals in the environment, and we got some surprises there, because although at the top of the rank we found the usual components of the contraceptive pill, we also found a lot of anti-inflammatory drugs and quite a few antidepressants and psychoactive compounds. Therefore, in the next two slides, I will share with you some of the work that we've done on neuroactive drugs, because this group of pharmaceuticals triggered our attention. So why neuroactive drugs? Neuroactive drugs are all those compounds that act on molecular targets in the central nervous system. And why they should be a potential priority for research? Because we hypothesize that this type of compounds may change the behavior of wildlife. And behavior is critically important because it controls virtually every single function of life, from reproduction to survival. So we know a few facts about neuroactive drugs in the environment. We know that according to the NHS, the mental health of young people, and not only, has been deteriorating in the last years. We know that the prescription rates of antidepressants and other drugs for mental health has been increasing year by year in the last probably 20 years or so. And all these prescription data are publicly available in the UK via the NHS, so that we can map with very high accuracy the geographical distribution of prescription rates across the country. Now, once we have all this data with us, what we did in our paper is we focused on 200 drugs act on the central nervous system. So what we did is we took all the NHS prescription volumes and we used this data to predict what is the concentration of the drugs that we would expect in the river in England. And once we did so, we did a further analysis to predict how much drug we expect to see in the blood of wild fish living in the rivers in England. At that point, we compared this information with the drug that we know is effective, with the concentration of drug in the blood of people that we know produces therapeutic effects. And the concept is fairly simple. The closer the concentration of the drug in fish is to the human therapeutic levels, the higher the probability that the environmental level of the drug in the river will cause pharmacology-mediated effects. So we use this as a proxy to assess the risk of these compounds. And using this approach, we ranked these 200 pharmaceuticals, and what we found is that more than 30 have some medium to high probability of being detected in the blood of wild fish in England, a concentration that is similar or higher that reported to be effective in humans. Therefore, this is a model that we use to bring some pharmacological concepts in the environmental risk assessment of pharmaceuticals. But do this concentration actually produce a behavioral effects. So in our work at King's, in our group, what we do, we leverage cutting-edge technology to advance our ability to assess drug safety assessment. So we show that antidepressants induce behavioral effects in fish as they do in humans, and they do so at comparable blood concentration. And to do so, we use sophisticated methods to track behavior. And here you can see the behavior of a larva that is in a control group, and this is the behavior of a larva treated with a drug that increases the activity of the animal. And you can see a clear difference. At the same time, we integrate this information with the analysis of the brain activity in larvae that have been exposed to pharmaceuticals. And this gives us further mechanistic understanding of the effects of these compounds in the environment. As you can appreciate, the complexity of these experiments that I'm showing you is increasing very rapidly. So we're generating a lot of data. So the challenge for the future will be to translate this biological complexity into a binary decision-making context. Yes, go or no go, stop the compound or not. At the same time, testing all these compounds that have never been tested before will require the use of thousands of hundreds of thousands of animals. Therefore, we need to develop novel methods to assess the safety of these compounds without running any animal test, using some cell in a dish or ideally computer models. At the same time, we have been considering one pharmaceutical at a time. However, we know the fish in the rivers and also human in the environment or any other environmental species is surrounded, is exposed to many thousands of compounds at the same time. And therefore, the main challenge here is to understand what the cocktail effect is. In order to address these challenges, we need to foster the collaboration between multiple stakeholders. And that's what we do at King's, working not only with industry, but also with regulators, public health authorities, and citizens. But in order to do so, we need to support, we need people with the right expertise. So we need to support toxicology education at global level for not only in laboratory-based toxicology, but also we need the training of people that they are able to translate scientific information into policy making. And at the same time, we need to increase the real world relevance of toxicology evidence to support ethically difficult decisions. And the question for you is, would you accept to stop using a given drug that has been predicted to have potential adverse effects in the environment? And would you ask your GP for a greener alternative? These are not easy questions to answer, and I'm curious to know your opinion. And that's all for me for now. And thank you. And I look forward to your questions.
Thank you so much, Luigi. That was a fantastic talk and with such clarity. I mean, I should say I'm a social scientist myself, so I don't know a lot of the details and the way the experiments are done, etc. But I really, really appreciated the ways in which you've been doing the various questioning and then talking about the challenges of understanding the cocktail effect. So this is really, really fascinating stuff. I invite our audience to put their questions into the chat. We're going to move directly into Carrie-Jean's presentation now. So if you have any burning questions, please put them on into the chat box. But once Carrie-Jean's presentation is completed, we'll also have a broader discussion and giving the floor to you, to the audience. So please do keep your questions and chats and in the chat box. All right, so I will now hand the floor over to Carrie-Jean.
Start by unmuting. Sorry. Hi, thanks for having me. I want to second Naho's comment that Luigi's presentation was really informative, and I think a really nice bit of science communication, and complements in many ways the work that I'm doing here, mostly in the United States, about reclaimed water. So I hope that you will bear with me as I just briefly go through with, I know this crowd is the water center, but I wanted to give this overview of the urban water system or the urban hydraulic cycle, a super simplified representation of modern sewerage and centralized waterborne waste collection and treatment in the city to kind of start my talk off. So I hope you'll bear with me. So In cities, we have our water supply represented here in the top left as, you know, maybe perhaps snow melt in a mountain into the river, which is extracted, treated at a drinking water treatment plant, and then it's distributed to the users in the drinking water distribution system for industry and household use. And then the water that's not used is collected in a wastewater collection system or sewerage, and it's transferred to a sewage or wastewater treatment plant. And there that is discharged into receiving waters, usually surface waters, and it carries on downstream. So of course, urban water systems are different everywhere you go, but this is the basic overview of what a modern water system is. And the variations in pollution loads that Luigi talked about means that the character of sewage varies really as widely as the quality of the source waters, the diversity of the surrounding industries, the consumption patterns of the community, including the drugs that they're intaking and excreting, right? And the standard treatment that's required by law before it's being discharged into that water system. And that in itself is all complicated by the economic and technical capabilities of the plant facilities and the surrounding community, their ability to, as ratepayers, pay for this infrastructure and treatment. So despite the diversity in watersheds and sewer sheds in the urban water supply, most modern wastewater treatment plants combine a common or conventional treatment train of processes to detoxify waste prior to discharge. In the United States, which is primarily where I work, we just celebrated the 50-year anniversary of the Clean Water Act regulations, which established the permitted and allowable amount of discharge into surface waters. And here in the US, most people are satisfied with their water providers and water quality. A recent poll, not done by me, a nationwide poll, found that people indicate 77% have a lot or some trust in their water utility. And so this is relatively recent, even given some also, like the UK, high profile water quality incidents. And 72% of those surveyed felt their water was safe. And though it's not directly related to water quality, it is and will be in the future. 32% of those that were surveyed said their water, they sometimes have trouble affording their water bills, or water affordability is an issue. So that's the typical modern water system. And this isn't my image. I borrowed this image and actually my title, which are that sewers are part of the water supply. So once we discharge wastewater into surface waters, those surface waters serve themselves as supply waters for downstream communities. So we're all downstream, or most of us are downstream from someone. Myself in Reno, Nevada, I'm very lucky to have the Tahoe River and the Truckee River coming from Lake Tahoe. So we have a small watershed, but the larger the watershed, the further downstream you are, the more wastewater or sewers are part of your water supply already, even if your city or community is not formally recycling water. They call that de facto or unplanned potable water reuse. So, but I really want to talk today about, and so that unplanned potable reuse happens in big, all over the world. The Thames, the Rhine, the Murray-Darling, the Mississippi, the Colorado River, all of these rivers contain sizable volumes of effluent or treated wastewater. So this unplanned potable reuse happens for millions of people across the world. But, and at times, this, as Luigi alluded to, we're proliferating in new chemicals, and also the contribution of wastewater is increasing in surface waters over time. And during drought, that contribution also can spike to a high percentage of what your water is if you're suffering a temporary disturbance or water shortage. So the actual percentage of wastewater contribution to the city supply is unknown sometimes. So now to my research interest, which is planned reuse of wastewater. So if we were to add another distribution system, we could imagine unplanned or non-potable reuse, where the supply comes in, it sends out in the drinking water, wastewater is collected, but instead of returning to the surface water system, it receives some additional treatment and is redistributed in a separate non-potable system for uses that are widely acceptable, like public irrigation of public parks, industrial uses, non-potable crops, and the like. So that's non-potable water reuse. Generally widely accepted, but it costs a lot of money to duplicate your delivery system, right? Your distribution system. So you have a whole separate set of pipes under pressure delivering a different quality water. So it can double the price and cause a lot of disruption, because remember, these pipes run under your roads. So if you didn't do this when you planned your city, you're going to be tearing up roads to put in a separate pipe system. So if you want to intentionally reuse water potably, you can also do what's called planned potable reuse. And that's where we collect that wastewater in a wastewater collection system. We treat it with conventional wastewater treatment processes, and then we add what we call advanced water treatment processes or tertiary treatment to clean it to a water quality that's fit for its next purpose. So if that's non-potable, right, that is a different quality than if it's potable. So if it's potable, we really focus on meeting the drinking water standards and removing contaminants of concerns and pesticides and pharmaceuticals and things that are left after conventional wastewater treatment. So advanced water treatment processes can remove up to 99% of the impurities in sewage. And so engineers would like to tell you that it's cleaner than what you're already drinking. If you're, can trust that in terms of water quality standards, that it exceeds in what comes out of your tap. So very briefly, you can do this directly or indirectly. Directly, just indirectly means we hold that water in an environmental buffer. So that is either a lake or a groundwater aquifer. And that gives us some time to do, or it gives us some treatment, some passive environmental water quality treatment, but it also gives you time to respond to any disaster or catastrophic event because you have some attenuation and retention time. Direct potable reuse takes out that environmental buffer and really takes water directly from the advanced water treatment plant and redistributes it to your drinking water system. So all of this type of reuse is illustrated by that purple in the center of this image, which purple is the internationally adopted color for water reuse. So generally speaking, people, like I said, trust non-potable uses or don't fear them and don't see them as a risk, but are very suspicious and tend to not accept potable water reuse. I cannot get my slides to advance. There we go. So advanced treatment technologies convert raw sewage, which is on the left, into drinking water, which is on the right in this image, by taking out the impurities, which is in the center. And the ladder of public acceptance, that's the proximity matters. Things further from us are more acceptable than things close to us, has been used to explain why people don't like drinking wastewater. They call it the yuck factor. And Paul Rosen, a experimental psychologist, uses the plastic roach in water as an explanation. He says, this association with sewage is disgusting to people. If I were to give you a glass of water with a plastic roach in it, you wouldn't want to drink it. Your disgust emotion and the contagion that is affecting that, and therefore it tarnishes that water from the public's point of view. And this view that the yuck factor or overcoming the yuck factor is really predominant in the literature and in the media when we talk about potable water reuse. And really, it's done in a way to say that the public is really lacking the expertise that experts have, that it's an illogical aversion to a really clean drinking water source, such as the plastic roach in drinking water that would be otherwise clean. But really, I think this is a good example to say what people's instinct or their common sense response is to drinking wastewater. Indeed, the law of contagion influences social, cultural, and psychological responses to toilet to tap, the other thing that potable reuse has been called. Even talking about poop and excrement is taboo in society. So to me, it's common sense that it's really to question the logic of why would we do this. So, and my research finds actually that people are much more skeptical than they are disgusted by the idea. Their first pass is to say, wow, that sounds risky, right? And risk is a probability. It involves some level of uncertainty, but it's also about relative risk and how risk is framed and debated. I'm here in Reno, Nevada, so I'm at risk of winning at the casino. Should I choose to gamble today, right? So to use Rosen's analogy, under the right conditions, I drink the roach water, right? And my students and people in the desert Southwest say, yeah, if I could trust the utility, that it was safe, that it exceeded my water quality, helped me survive a drought, or it was better for marine life or other animals, or it saves water for other people, et cetera, I drink the roach water. On the other hand, if it's just going to contribute to sprawl and urban growth and increased costs and mean years of construction and tearing up roads and a real decrease in my quality of life, I can easily access the toilet and the toilet to tap imagery as a way to oppose these projects. So I would say, in my view, the yuck factor is really overstated, that acceptable risk is a political assessment, that people accept it in many places. In fact, potable water reuse is the water for the 1%. It's an incredibly expensive process. It is safe, but it really relies on a number of social and technical components to be done right. The collection of sewage in underground pipes, linked to treatment plants, and legislative controls that prescribe necessary treatment and monitoring, and administrative staffs in charge of oversight, and the operational staff who can deal with the disposal of these products, right? All of these things are really complex and should and do are faced with some level of skepticism by the public. So I'd say, in order to overcome this yuck factor language and to advance public acceptance and trust, is to get over the flush and forget mentality and start recognizing that sewers are part of the source water or part of our water supply, and have those discussions that Luigi was talking about. Would you stop an environmentally destructive behavior if it meant a better outcome for you or society or the critters or whatever is really meaning to you in your environmental ethics? So with that, I should stop, because of course I could go on forever.
Well, thank you so much, Carrie-Jean. I really love the sort of phrase that you had as sewers as part of water supply. I think it really hits home the fact that we really need to have a more holistic understanding. And the fact that you said that the yuck factor is overstated, it's a really interesting insight into how these technologies and societal perception and the political costs, etc., all come together in this single story of water reuse. So I think we've had two very fascinating talks. I've made plenty of notes on my screen. I've been scribbling away, but I'm sure the audience would also love to ask some questions. I think some conversations have already started to go on in the chat, but I want to give the floor to the audience. If you would like to raise your hand using the palm button, you can do that. You can also turn on your screen if you are able to. I'm really delighted to see a lot of familiar names, old friends, as well as new friends joining our event today. So the floor is yours. Are there any questions for both Luigi and Carrie-Jean? I wonder, since there's no palm hand that I can see, Luigi, do you want to expand on the first question that was actually by our colleague Daniel, who talks about the types of pharmaceuticals, 975 pharmaceuticals, and how you're looking at those?
Yeah, absolutely. We may get a little bit technical here, but in simple words, there are different types of therapeutic modalities of pharmaceuticals. The pharmaceuticals that are typical in the environment are called small chemicals or small chemical compounds. At the same time, other types of pharmaceuticals that we have, in particular in recent times, are antibody type pharmaceuticals or some biologic components able to modify DNA or RNA and so on and so forth. But those have lower risk because they are specifically for humans. So the number that I mentioned in my presentation refers to all those small chemical pharmaceuticals that act on human proteins as classified by a database that is, I think, run by some colleagues in Canada that is called Drug Bank. Overall, the number of pharmaceuticals in the market, there are several estimations, so it's difficult to get a precise number, but it's anything between 1,000, 1,500, including all therapeutic modalities, but it is difficult to track the exact numbers worldwide because there are different registration processes in different areas of the world.
Great stuff. Thanks so much. I just noticed there is a new comment in the chat box, which is going to Carrie Jean. So this comes from Tia, one of our PhD students. Oh, and Carrie, you've just perhaps responded to that, but would you like to expand more on your response about the public perception, the American public perception on water supply? I think you said that many people, 70+ people, trusted their water, but there were some challenges of water affordability.
Yeah, so I would like to say that sewers as part of the source water, I stole that from somebody who's much better at science communication than me, Harris Lovelet and David Sedlak. And that data comes from the American Water Works Association, which is essentially the research or the association of public water providers for the US. So it's not surprising, my research finds that people have a very high trust in academics. So often, the way that you survey or the person who is doing the survey research finds that people who trust them respond to their surveys. So I can't speak to the true accuracy of that survey because we know that there could be some bias there. But really the truth is that research has found that generally speaking, Americans do trust that their water is safe, even despite very public water system failures, and that water contamination is often invisible, has no scent, right, and should be questioned in some instances. And that same data found that 32% of folks that answered the survey struggle to pay their bills on time. And that's really of concern, given that if we want to take the treatment-based approach rather than a preventative approach to pollution, then it's going to cost a lot of money. It's going to cost a lot of money in infrastructure. It's going to cost a lot of money in energy. It's going to be operations and maintenance for the lifetime of these plants, and that's going to be pushed down to the ratepayer. So people will have to pay more for water. In some cases, that's better quality, but in some places, that's not better quality, and you'll still be paying more. We also have the conservation conundrum when it comes to water, that the more you save water in the household, it can drive the cost of water up for you. And it also increases the pollution load. So you have more concentrated pollutions at the wastewater treatment plant, which increases the cost of treatment. And any conservation, of course, captures your recycled water, your parent supply to recycled water. So it's a very complex, interconnected system. So we really do, I think, behoove us to think about prevention as the primary stewardship approach rather than treatment when possible.
Yeah, I think this point about affordability and how much money people are paying out of their household budget for water is a really interesting one. And at what kind of quality, I think that's a really interesting debate, not just happening in developing economies, but also in developed economies as well. So a really interesting point again. Daniel, you had a follow-up question. Do you want to put your microphone on and speak if you wanted to have a bit more interaction, or should I read it out?
Yeah, I can do. I'm on the train. I'm not quite home yet, so but hopefully you can hear me all right.
We can hear you very well.
Yeah, okay, great. Yes, thank you, Louis. Well, both talks were fascinating, but yeah, Luigi, on your last slide or two, you talked about feeding this into policy, and I just wonder if you could say a bit about sort of where that's up to. I've heard a bit from you today and a little bit in previous talks, but I don't know how conscious policymakers are or environmental managers are of this hidden pollutant or hidden contaminant. So it might be interesting to hear how far along that journey you are, or you and your colleagues are.
It's a great question, Daniel. Thank you. Which is actually the critical point here, because science is great, but until it's not translated into policy, the impact of our research is going to have very little effect. So at European level, the Water Framework Directive provide the policy support to manage the potential presence of selected group of chemicals that have high priority because they've been demonstrated to be to induce potentially some troubles in the environment. So it tells to member states what chemicals they should monitor regularly in the monitoring programs in order to assess, if you like, and monitor, to do what we call the eco-pharmacovigilance, at least for pharmaceuticals. I think some of these chemicals include, there are different tires in the list, ethinyl estradiol and estradiol. There are two of them, so estrogenic compounds. And then for a short while, we had the anti-inflammatory drug, the clofenac. And then lately, its chemical of interest is the anti-diabetic compound metformin. At different level, what we have been observing is that there has been an increased level of collaboration between pharmaceutical industries and academia and regulators in order to speed up the overall assessment of these compounds. Because as you can understand, the cost-benefit assessment for a pharmaceutical is very different than the one that you apply for example, in industrial chemical in your plastic bottle. Because there are some ethical aspects that need to be considered for the protection of human health and treatment of disease. But there is this integration between multiple stakeholders, and we at King's, we are part of it, that is speeding up the process with enhanced transparency. For example, a company that we worked often with, like AstraZeneca, pharmaceutical company, has a website where you can go to see all the safe levels and the ecotoxicity studies for all the pharmaceuticals that they sell, and it's publicly available. And there are many projects, large projects at European level involving also regulators as partner in order to speed up the policy translation, if you like, of our research.
An interesting point about also thinking about the costs of doing all of this, because you could probably look at all sorts of chemicals if you wanted to. Luigi, could you just say a tiny comment about forever chemicals, because that's been in the news here in the UK. And I wonder if you could explain to the audience how these forever chemicals are, why it's starting to come into the public domain to discuss.
Typically, when our ability to detect these compounds in the environment has increased dramatically in the last 10 years. So this technical ability is opening a lot of new avenues, because we realize that any chemical you may think about, most of them are in the environment of some sort. And of course, when there is a mounting of reports about environmental occurrence and maybe uncertainty about their toxicity, I think that's mainly what trigger a public health concern, where you have something that is there, but you don't really know enough to understand whether it's toxic or not. And then I think, in my opinion, work as an engine to to foster and kickstart these mounting initiatives towards a specific group of chemicals. But what you mentioned earlier is exactly the point. There are thousands of chemicals in the environment. So the question that we need to work together on is, how do we prioritize which is the chemical that we should focus on, or what group of chemical we should focus on?
Great stuff. Thank you so much, Luigi. There's a question from Malcolm to Carrie Jean, and it's about, if money was available, would granular activated carbon treatment be the go-to treatment scheme that a wastewater treatment plant could utilize to capture these contaminants, pharmaceuticals? Would you be able to make a comment on this? Would you have any insights on this? And also, just piggybacking on that, how high is prevention on the political agenda, as it were?
Ooh. Okay, both of these questions. Okay, the first is a little bit far out of my field of expertise. I will say that it is a treatment process that's not utilized widely, but I think that is the one that is used in Namibia and is in El Paso. It's being used more in inland where reverse osmosis is not as viable because of the brine stream. But that is, I'd have to go to the literature for the pharmaceutical and to really get at it. But I do believe so. And I think if I had more time, I'd look in this new book. If you're really interested, there's a new book called The Water Recycling Revolution by William and Rosemary Alley. That's mostly about the United States perspective, but it brings up a lot of the different types of treatment train and water quality kind of approaches by different municipalities and different places facing different water quality constraints. So if you're interested, and maybe I'll take your email and see if I can get a better answer, but that's the best answer I have on the fly. And then the preventative approach, you don't hear much from it. The one good thing I will say about, I have read, I think I even read it in that text about indirect potable reuse, is that it does put a little bit more of a tightening level of observation on your industrial polluters in your community. If there's a spike in a certain chemical of concern, it's much more likely to be noticed by your wastewater provider if they're actually looking for that in their advanced water treatment processing, or about, so oftentimes those things go unnoticed, and they're likely to get noticed in an instance where you have potable reuse. So I would say that. But in terms of real prevention, like upstream regulatory prevention, I don't hear much of it in my field, but that's not to say that it's not happening.
Okay, great. Thank you for those responses. And I think, Katie, you have a question for both our speakers. I think we do have time to ask quick questions, so go for it.
Great. Thank you both, Luigi and Carrie Jean. This was fantastic. So both of you have unique and interesting insight into this institutional landscape of water quality. You've talked about the public, you've talked about the private sector like industry and the pharma companies, and policymakers, but I'm really interested in your views on water utility, the providers, the companies, if you're here in the UK. What have you seen their role in this sort of institutional landscape of understanding these contaminants of concern, but also sort of managing them? Like, how do they fit into this landscape?
Luigi, you want to go first?
That's very, very good question, Katie. I mean, I'm not a field scientist, but I remember when I was doing my research at Brunel University, London, Thames Water was often a partner of the research carried out to understand the potential risk of endocrine active chemicals in the water. So there was a lot of collaborative work done with Thames Water and scientific projects and so on and so forth. So I'm sure that I suppose that many water companies probably have some sort of activity, but I'm not familiar with the policy translation. So I don't know what role they play, and I suppose they do play it. I don't know what role they play, in terms of policy translation. the cost, when there was a story of ethinyl estradiol and the contraceptive pill and the effects on wild fish, which was a very dramatic effect because, you could potentially having eggs in the testes of a male is one of the most dramatic environmental effects that we are aware of in terms of pharmaceuticals in the environment, in the aquatic environment. And there was a lot of discussion whether we should upgrade the wastewater treatment plants. And the predicted cost was extremely high. And so the question was, should we upgrade all our wastewater treatment plants for one single compound? Or there could be better management, approaches that we could use to mitigate the risk.
I think it's hard to say with a lot of confidence across utilities. I'd say in the Western US, there's a lot of interest in reclamation. And with that, there's the recent bipartisan infrastructure bill. So there'll be a cash infusion like there hasn't been in two water utilities in the United States. And so I hate to say it, but I get the feeling, though I don't have a lot of empirical evidence, that there's more of a techphilia going on right now, and that there's an ability to pay for new cool tools that will eliminate a lot of contamination and be this like cool, like if you've ever been to an advanced wastewater treatment facility, it's fantastic. I mean, it really is dazzling to see raw sewage transformed into clean drinking water. And so I do think that there is a lot of hubris in this water recycling revolution, that actually reuse will be the provider of the future. I'm a little less optimistic. I think the water recycling revolution is a different type of revolution, just more of a circling around the same ideas and less of this much more preventative approach that would be more inward looking and cost a lot more, maybe politically, socially, behaviorally, than the equipment costs of potable reuse. But that's, I don't know, catch me on an optimistic day, I might feel differently. But right now, yeah, I just feel like it's too many cool tools. The fact that we can do it is just really attractive to water utilities.
Yeah, that's a really interesting insight about how we might be sort of focused on the technology, and then there's all that socio-economic political considerations that also need to be made. And
how would you do that? We can't imagine. It's really hard to imagine how to do that. And now we have concrete equipment that can show us how to transform waste into drinking water. So that looks pretty cool, right? That looks like a reasonable solution to most utilities, I think. When you bring up real core preventative strategies, even using the emerging terms that they like regeneration or green networks. But if you get to kind of a much more rooted preventative, you sound like a heretic.
Yeah. It's really about fundamentally changing the way societies operate if we were really, really wanting to change it at the upstream. So yeah, no, I can definitely see that this would be a very inconvenient sort of reality that many parts of society would have to face if we were to go down that road. Yeah, very interesting stuff.
Now, if I can follow up just very quickly to these points, I think what also we need to consider that is the environmental risk assessment of these compounds or of any chemical needs to be a live document that will change with time, because the environmental, socioeconomical conditions will change. If we think about the change in water availability around the world, and not even in far distant places. I'm from Italy, and for example, in the south of Italy, there is a significant process of desertification sometimes. But even in the UK, sometimes in some periods of the year, some rivers are dominated by the effluent of wastewater treatment plants and not by water. So it's one of the countries where you see a more a bigger difference in the sense of dilution. So there are some periods of the year where the effluents in some streams represent a dominant component, whereas this is not true in other countries. And this thing with the changes in the way the climate changes will change with time. Therefore, we cannot think that what we know. So what we know today needs to be used to predict what happens in the future. So we need to implement predictive strategies in order to tackle the challenges with time.
Very fitting, Luigi. You've just made everything all the more complex. No, but this is a really great, I think a very interesting conversation to continue because of the fact that, as you say, things are dynamic, things move. It's also very context dependent. It's sociopolitically charged as well. This debate about water contamination and what's acceptable, what's appropriate technology, what's palatable culturally, what's seen as risk, I think is also something that needs to be worked out through different partners, not just the science community, but also with policymakers, utilities, businesses, etc. So I really find this a topic that I think will have a lot more interest, a lot more scrutiny in the future. We have a final couple of minutes. I just want to do a final sweep of the chat box to see if there are any final burning questions. Please do feel free to push the palm icon on your screen.
While Naho does that, I'll just say I'm Katie Meehan. I'm the other co-director of King's Water Center, and we're really pleased with to both Carrie and grateful to Carrie Jean and Luigi for kicking off this series that we hope to continue in the upcoming months of getting great brains together to talk about complex and wicked problems in water sustainability. Just to signpost a few events that are coming up with King's Water. The geography department at King's College is turning 100 next month or this year. And there will be celebrations going on with King's Water Center as well in November. So come join us if you're around. We expect to have some more policy briefs, which were really successful that we launched last spring. So don't be surprised if you see these rolling out in the next few months. And of course, the Tony Allen Memorial Lecture, which will happen in spring 2023 as well. We have a couple other things cooking on the fire, but we'll kind of release that when we're ready. But as ever, thanks very much to everyone. And please join me in thanking our two wonderful speakers for a really insightful and compelling and fascinating and also horrifying presentation. Thank you very much, both.
Well, I don't see any further comments in the box. So I'd like to also add my thanks to our two wonderful speakers, Luigi and Carrie Jean, for these insightful, short lightning talks. And, you know, by virtue of joining us on this website, I really welcome you as part of our King's Water community. So please do keep in touch with us. Please engage with us. If you have any good ideas of seminars, webinars that we want to put on, please feel free to reach out to us and tell us, hey, this is the kind of question that I want answered. Can you help? I mean, we would love to have conversations like that with you. So you're part of the community now. So look out for an email from us. Thank you very much. And bye-bye to you all.
Thank you.
Lacey, thank you so much for your help. We're able to stop recording.